next test we're going to look at is the ratio test for positive series. But before we do that, there's a couple of useful facts that you want to be aware of. And we're going to be looking at some series that involve factorials, so it's a good idea to go back and remember what a factorial expression is. So the first fact we have here is what is k factorial divided by k plus 1 factorial equal to? Let's do a numerical example first. So let's suppose we were talking about k being the number 4. In that instance, we would have the expression 4 factorial over, and then k plus 1 factorial would be 4 plus 1, or 5 factorial. Now, what factorial means, remember, is you are writing out the terms of the factorial starting with the number of the factorial, which is 4, decreasing those terms all the way down to 1, and then multiplying them together. So in the numerator, we have 4 factorial. In the denominator, we start at 5 and go down 1 each time, and that's 5 factorial. And what you'll notice is that 4 factorial is actually contained within 5 factorial. So we can cancel all of those factors out, leaving nothing in the numerator except for 1. And the denominator is 5, which is the same as k plus 1. So in other words, when you have k factorial, that's made by writing out the terms k times subtract 1 from k times subtract 2 from k, all the way down to 1. When we write out the terms of k plus 1 factorial, we're starting at k plus 1, multiplying that by k, multiplying that by k minus 1, and so forth, all the way down to 1. It will always be the case that the factorial in the numerator, all those terms, will be contained in the denominator, allowing us to cancel them out. So this is the same as 1 over k plus 1. That's the first fact you're going to want to know. Now, the other useful fact is when you have addition within an exponent. Where that came from, remember, is the rule that said when you have two expressions with the same base that are being multiplied, you can add their exponents. You're used to using this rule predominantly in the reverse order, where you take the two expressions with the same base and you add the exponents together. We can also use that rule in the other direction, allowing us to split an exponential expression with addition in its exponent into two terms that are multiplying each other. So this is the second fact you're going to want to know today. Now we can get into the ratio test for positive series. And the ratio test is going to remind you of geometric series because we're going to be forming the ratio between successive terms. We said a geometric series, which looks like this, converges if and only if that ratio of successive terms, the absolute value of it, is less than 1. The ratio test is going to be very similar to that. Because notice what the ratio test for positive series says. First of all, it says suppose that all your terms are positive, greater than 0, for all k values, and that the limit as k approaches infinity of, and this is the ratio of two successive terms, a sub k with the one that comes after it in the numerator. So suppose you're able to figure out that limit and it's equal to L. The value of the L will tell you what the series is going to do. If L is less than 1, the series converges. If L is bigger than 1, the series diverges. If L equals exactly 1, then this test is inconclusive, meaning we don't know if the series diverges or converges based on this test. And the ratio test works best for series in which the index k appears in an exponent or a factorial. So the integral test works when you look at the expression that forms the series and it's something relatively easy to integrate. Ratio test works for these two situations. So we'll look at a couple of examples. It's the first example says show that the series k equals 0 to infinity of 1 over k factorial converges. Guess its limit. Because we see the k value in a factorial, that's what should cue you to think about, oh, maybe this is ratio test. So we have to verify that all our a sub k terms, which are based on 1 over k factorial, are going to be greater than 0 for all k values. Well, k is only taking on the values from 0 to infinity, and you may or may not remember it, but if you do plug in k equals 0 here, 0 factorial is defined to equal 1. So even when k equals 0, this does have a value. And then the second thing is, are all these terms going to be positive? And the answer is yes, because factorial expressions are always positive. So since all my terms are positive, and again, the fact that k is in a factorial, I'm going to apply the ratio test, which involves taking the limit always of a sub k plus 1 divided by a sub k, a term divided by the term before it. So literally all you're going to do in the first place is the numerator, you're letting k take the value k plus 1. So I go back over here and I just replace k with k plus 1. I do that on the left and I do it on the right. So my numerator will be 1 over k plus 1 factorial, and my denominator will be just a sub k, which is 1 over k factorial. Now, because we're taking the ratio of things that are themselves fractions, what you're going to want to do next is say, okay, this is a fraction divided by a fraction, which is the same as keeping the first fraction the same, changing division to multiplication, and flipping that second fraction. Now, it's important, and this I always do this, you really should have limits every step of the way here. So I'm going to sneak one in there, and I technically need to sneak one in right here. So we're looking for the limit as k goes to infinity. I have 1 times k factorial in my numerator, which is k factorial over k plus 1 factorial. And now we have that fact up above, which says all the terms of this k factorial will be contained in k plus 1 factorial, and they'll end up canceling each other out. And the only thing that will remain is a k plus 1 in the bottom. So again, I'm using that fact we referenced above to get from here to here. And now we can take the limit. As k goes to infinity and gets to be bigger and bigger, it goes from 1 to 2 to 3 to 1,000 to 1,000,000, the entire fraction, when the denominator gets large, goes to 0. Once I know this value, I know the value of capital L for this particular instance of the ratio test. Now I go back to my test and I look at the 3 different possible L values. I'm looking at the first case. My L value is 0, and 0 is less than 1, so I know that my series converges. So I would say since L equals 0 in this case, and L is therefore less than 1, the series k equals 0 to infinity of 1 over k factorial converges. Now, it says guess its limit. In order to do that in a convenient sort of way, we'd want to look at the partial sums. So I'm going to bring in Mathematica just to make that easier. So here in Mathematica, I've defined my partial sum and I've created a table. And you can see in the table here that the limit of the partial sums is going to what is hopefully now a familiar number. 2.71828 are the first several digits of E. So it turns out that this is a series that converges to E, which again, there's just many different places where E shows up that are kind of unexpected. So to finish off this problem, I can say that the limit as n goes to infinity of the partial sums goes to E. And we'll do one more ratio test example here. So first, we need to check that our terms of our series, which are generated by 100 to the k power over k factorial, are going to be greater than 0 for all k values. And that should be relatively easy to determine because, again, we're substituting k values from 0 to infinity. So yes, each term is going to be positive. Now I can apply my ratio test, which says take the limit as k goes to infinity, always of a sub k plus 1 divided by a sub k. Now I already have what a sub k is equal to. I just need to figure out what a sub k plus 1 is, simply by replacing the k's with k plus 1's. And now I have the two things I need to substitute into my ratio. So I will have the numerator is going to be 100 to the k plus 1 over k plus 1 factorial. And that's divided by 100 to the k power over k factorial. And notice me forgetting my limits again. Good job. I'm going to carry that limit through. And remember, dividing by a fraction is the same as multiplying by its reciprocal. So we'll keep the numerator of the original fraction the same, change division to multiplication, and flip the second fraction upside down, which gets us here. What I'd like to do is swap these numerators around. So I'm going to go ahead and do that because multiplication is commutative, so certainly that's a legitimate thing to do. So I'm going to have k factorial over k plus 1 factorial. And then times, if I swap, it's 100 to the k plus 1 over 100 to the k power. Now here's where we've got those facts again that we saw from above. The first fraction in my limit expression here is just going to reduce to 1 over k plus 1. And the second fraction, here's where you want to use the second fact that we talked about, how if you have addition in the exponent, you can write that as a multiplication statement. And the reason we'd want to do that is we can split it up now to two things that are multiplying each other that have the same base. And you can see I now have a common factor of 100 to the kth power that I can cancel from the numerator and denominator. So my limit is now, I have 100 in the numerator times 1 over k plus 1. And when we allow k to take on larger and larger values, even though the numerator is 100, it does not matter. This is still going to head to 0. So that means that my L value for the ratio test is 0. And as we saw before, when you get an L value of 0, your series converges. And in this case, we're not asked what it converges to. So that's how you apply the ratio test. And you can see why those two facts that we started with are particularly helpful.